So welcome back to the second lecture on multivariable calculus. In the previous lecture, we have defined norm and we defined equivalence of norms, and we showed that on Rn, two norms are equivalent. And in particular, any finite dimensional vector space also, any two norms are equivalent. That means any two norms on a finite dimensional vector space, they will induce the same topology. Okay. And okay. So now onwards on Rn, we will always uh, fix this L2 norm. Okay. On Rn, we will always fix usual L2 norm. The usual L2 norm. Okay. So okay. Now let us. Okay. In previous lecture, actually, I have really given a question why L2 norm is defined like that. I hope you have found the answer. So answer is the following. So if you look at, so suppose 1 less than equal to p less than infinitive. And if you look at this thing, limit p tends to infinity norm of xp. So that is really not, okay. So this will, you can show that this is nothing but maximum of 1 less than equal to 1 and modulus of xi. And for this reason, actually, we define. So since limit p tends to infinity, norm of xp is maximum 1 less than equal to I to n norm of xi, we define this thing norm of x infinitive to be this thing maximum of 1 less than equal to I less than into n modulus of xi. One thing you just you should understand that in mathematics, when you write this notation colon and equality, so that means that this notation is used whenever you define something. Okay, so coming back to today's lecture. Okay, so in the previous lecture, actually, I have proved this thing that any two norms on Rn are equivalent. Okay, and I have proved that thing. And observe one thing, actually, what is the meaning of any two norm equivalent? I have to prove. At the end, I have proved this thing. So in particular, uh, the okay, so recalling the proof of the fact that any two norms on Rn are equivalent, we have proved that first that any norm is equivalent to L2 norm, and then we have proved that any two arbitrary norms are equivalent. So while proving that any two norms are on Rn, any norm on Rn is equivalent to L2 norm, so one needs a relation like this. So so this thing norm, any norm is equivalent to L2 norm, amounts to showing something like C1 norm x2 less than equal to norm x less than equal to C2 norm x2. Okay, okay. So this we have to show this norm is equivalent to L2 norm, amounts to proving this line. But the thing is, one side of this thing, this side, actually we have already proved previously. Okay, so we have proved here. Okay? We have proved in A. Okay, so what I'm saying that okay, so that means this one side actually is not needed actually for the proof, but I have given deliberately kept this other side for some reason, so which we will understand in the later classes. Okay, okay. So what I'm saying that this any norm is equal to L2 norm amounts to proving this line. Okay, but the thing is, one part of the line. Okay, so this norm x is less than equal to norm x2. We have already proved in the thing is we have proved somewhere before. in A. So the thing is, okay. So that one part is not needed technically in the proof, but I have kept it in deliberately in this thing. Okay. So another thing, while proving this, I have given you only the proof of this result that any norm um, uh, is equivalent to delta norm, but I have not explained you the idea of the proof, why one why the proof is like this. So you have to think about it. Okay, so the thing is, you should understand that in mathematics, that verifying a proof, it is not really uh, is mathematics. Okay, we have to understand the idea of the proof. So you just should think that about the proof, uh, this proof once more. Okay, go into the inside the proof and find out the idea of the proof. I will just tell about the idea in a later lecture. Okay, so let us move. Okay, okay, okay. So so on Rn we will always fix the little L2 norm. Okay, this is the thing. Now let us begin with a definition. Okay, so this is little o notation or big O notation. So let f be a function from Rn to Rm, and g is a function from Rn to Rk. So m, n, k are different. Okay, okay. So we say that, okay, first thing, this fx is equal to little o of gx as x tends to a. Okay, if so, limit x tends to a, fx norm of fx by norm of gx goes to 0. Okay, so we say that fx is little o of gx as x tends to a if limit x tends to a, norm of fx by norm of gx is equal to 0. And okay, so this is called little o. Okay, okay. So the thing is, and here assumption is what is the assumption on g? Assumption is d x not equal to 0 on a neighborhood of a, because we are dividing norm of gx. This is the standing assumption, neighborhood of a. Okay, okay. So second thing is, we say that, okay, so we say that fx is big O of gx, big O of gx, if limit x tends to a, norm of fx by norm of gx is less than c. Okay, for some constants where c is a constant, where c is a positive constant. Sometimes while writing, so sometimes people make this big O, small o, the size. So small o, size of small o should be smaller than big O. But while writing, sometimes people become careless, and sometimes they mix these two symbols. So students get confused with these symbols. So for that reason, actually, I will, whenever I will write big O, I will put a bar so that you will understand this is big O. So this is the big O notation. Okay. So as here also as x tends to a, you have to write, and you have the similar assumption about gx, because you are ultimately you have okay. So this same gx is not equal to 0 on a neighborhood of a. Okay, okay, okay. So this is the thing. Now small exercise or observation. This exercise. So suppose let f1, okay, x is equal to epsilon of gx. Okay, and what is epsilon? Epsilon is either small o or this big O. Okay, big O. And this f2x is really epsilon of gx. So okay, as say x tends to a. Now this will then so that this thing then this f1x f1 plus minus f2x. Okay, this is really this is epsilon of gx. Okay, so if and where f1 and f2 are function from Rn to say Rm, and G is from Rn to Rk. Okay, okay. So the thing is, if f1 is of little o of gx and f1x is little o of gx and f2x is little o of gx, then their sum f1 plus s2x is also of little of gx. Similarly, you can uh, think that similarly this happens for a big O of gx. Okay, now let us so this is a small exercise and it is a very easy exercise. So now let us move. Okay, so let us discussion. Okay. So the thing is, okay, I will use short one notation LO for linear operator. Operator. Okay, linear. Okay, so let us call this LM. LM for linear map. Okay, so let notation. Okay, this is notation. This L. Okay, so this is thing is L Rn comma R set of all linear maps from Rn to Rm. This is the collection of all T mapping T from Rn to Rm. So that T is linear. Okay. Okay. Now this Rn comma Rm is identified, can be identified with MNR. So this LRn comma Rm, you know that from linear algebra course, this can be identified with MNR. Okay. And what is the identification? So if you look at this any element matrix, okay, so a matrix from A belongs to MNR, so that will give rise to a linear operator PA from Rn to Rm. Oh, sorry, my mistake. So from your linear algebra course, LRn comma Rm is nothing but M cross NR. So what is M cross NR? So this is the collection of all M cross N matrices with real entries. So any element of M cross NR will give rise to a linear operator from Rn to Rm. And what is the linear operator TA? So TAB is simply this is AB. So this is just matrix multiplication, and this B you have to treat as a column vector. Okay. Okay. Now similarly, if you look at this thing T, linear map from, and you know that, okay, from the linear algebra class, you know that this is a bijection. Okay, this ln Rn comma Rm is nothing but M cross NR. Okay, this is bijection from the linear algebra class, you know. Now, okay, so when n is equal to m, okay, I will write just LRN. So LRN by definition is what? Uh, by definition, this is really LRN comma Rn. So the linear operators from Rn, comma Rn, and this is nothing but M n R. This is the n by n real matrices with n real entries. Okay, now you look at this element LR. So LR by definition, this is really this is M1R. This is the 1 cross 1 real matrices, and this is nothing but R. Okay, you can identify that. So any real number R can be thought of a linear map from R to R. And what is the linear map? So what I'm saying, linear map um, from R to R. So if you look at this thing, so say let us say A is an element here. So it will give rise to a linear map TA. Okay. And what will be TA? TA will be just simply multiplication map. So TAB is equal to AP. Okay. Okay. Now conversely, if you look at any linear map from R to R, so that means the T of B is equal to what? Um, T of B into 1, and B is a scalar, so it can be pull out B into T1. This is T of 1 into B. So that means T is also a multiplication map. Okay. T of B is multiplication by T1. So T will be mapped here. From here, you will be uh, getting a map from T to T of 1. So this is the identification. So so real number R can be thought of a linear from R to R. Similarly, and what is the linear map? That this is just a multiplication map. Conversely, if you look at any map from R to R, and suppose that map is T going to T of 1, that is the bijection between R and LR. Okay, so we will remember this identification. We will use this thing later. Now this thing is going to back to this thing. You look at M. Okay, so L Rn comma Rm. Okay. So this is nothing but what? This is really MNR. M cross NR. So M cross NR can be identified with RMN. Okay. So what I'm saying, L Rn comma Rn can be identified with M cross NR, which is nothing but RMN. Okay. Now take. Okay. So the thing is, okay, we know that this RMN has a natural norm structure. So we can really borrow that norm structure to M cross NR. So in principle, we can borrow that norm structure to LRN, Rm. Okay. So RMN has a natural norm structure, that is the usual L2 norm. So we can borrow that norm structure. So what I'm saying, if A belongs to MNR, M cross NR, so I can define a norm. So if supposing this A is equal to really Aij, so I is less than, okay, so I is less than equal to 1 to M, J is less than equal to 1 to N, then norm of A, oh, yes. So norm of A you define like can be defined as like this, Aij norm square Ij to the power half, where I varies from 1 to M and J varies to. So this norm is has a name. This is called Hilbert-Smith norm, or sometimes people call this as Forbenious norm. So it stands for Hilbert-Smith norm, or sometimes people call this as Forbenious norm. So what I'm saying that LRN comma RM has a natural norm on it, that is Hilbert-Smith norm or Forbenious norm. So if you are really bothered about this course, if you are only bothered about developing calculus on RM, then one can really work with this Hilbert-Smith norm, okay, or Forbenious norm. But there is something called calculus on non-linear space. But to develop calculus on non-linear space, develop calculus on non-linear space. See this an infinite dimensional non-linear spaces. This norm is not useful. So there is another norm which is natural norm is there. This is called operator norm. That is a very useful norm. So we will you study that norm first, then we will see something. Okay. So I hope these things are really clear to you. Let us uh, go to study that now. Okay. So okay. So now you know that on RN you have really a, you always equip with L2 little L2 now. So a little bit of discussion. Okay. Let us see the question. First question is, so let T from Rn to Rm be a linear map. So is it true that S is T is continuous? Okay. Okay. So okay. Okay. So we will discuss this question first. Okay. So we will answer this question first. But let me state you something which I probably may. Okay. So okay. So let us see. Okay. So I will prove this thing. Okay. So let us. Um, okay. So let us answer this question first. Okay. Answer is yes. Okay. So let us do a little bit of discussion. So let T from Rn to Rm be a LM. LM means linear map. Okay. Okay. LM stands for linear map. Okay. I have told you something. Okay. LM stands for linear map. Okay. So the thing is, if you look at this thing, T of summation of I is equal to 1 to n xi ei. Okay. By since T is linear, so this will be I is equal to 1 to n xi T of ei. Okay. Now I can take the norm both sides. So this will be this thing. Okay, so okay, what is x? X is really nothing but x1, x2, xn. Okay. So okay, so this implies this is okay. So this is okay. Left hand side is just tx norm. Okay, so okay, this is okay. Left hand side tx norm. This is equal to this. Now this. Now I can apply the triangle inequality here. So this will be less than equal to. So summation of I is equal to 1 to n xi T of ei. So this is by triangle inequality. Okay. Okay. So this I and apply the homogeneity. So this is I is equal to 1 to n. This modulus of xi norm of TEI. Okay. But this modulus of xi is this always less than L2 norm of x. This is clear. Okay. So this is this is less than equal to. So if I will use that thing, so this is really I is equal to 1 to n norm of x2 norm of TEI. So this is equal to m into I is equal to 1 to n norm of x is 2. So what is m? M is nothing but norm of T1 plus norm of Te2 plus norm of Ten. Okay. So that is the m. So what I am getting here, so norm of Tx is less than equal to m into norm x2. And this is for all x belongs to Rn. This Tx is an element of Rn, so this norm is an L2 norm of this norm is an L2 norm of um, Rm, and but right hand side is just L2 norm of Rn. Okay, so this I should not write here 2 here. So this is always okay. So the thing is, it call this is really a. Okay, so I am getting T norm of Tx is less than equal to m into normal. Just excuse me for a second. I will drink a little water. Okay, so from this A we will get this thing. In place of x, if I will put x minus y, what I will get? So T of x minus y norm is equal to less than the m, the norm of x minus y. So this will imply that Tx minus Ty is less than equal to m into norm of x. So the first conclusion, so x going to Tx is conclusion is T is a continuous map. The linear map T is continuous. Call this is C. So conclusion from C, it follows that the linear map T is continuous. Okay, so we have proved this thing, T is continuous. Now, okay, so okay. So now okay, so definition. So this answers the question which I have really in the beginning. So definition. So okay, before giving the definition, we have so okay, from A we have this thing. So we have so okay, let us make two conclusions. So first I and second, given a linear map T from Rn to Rm, there exists a constant, so m greater than 0, so that, and this is finite constant, so that this thing happens for T norm of Tx is less than equal to m norm of x for all x belongs to Rn. This happens. Okay. So call this as star. Okay. Now, okay, so we define, so T is a linear map. So definition. I define this thing, norm of Ts. Okay, so I am calling it this is norm of T. Yes, but without proving that is norm. Okay, so we will prove this thing later. So norm of Ts is really, supremum of Tx. Okay, this is norm x less than equal to 1. So this is nothing but supremum over norm of Tx, where x varies with on the unit sphere with center at origin and radius 1. So norm of Ts is supremum of norm x is equal to 1, norm of Ts. So I define something similarly. Norm of Tb is equal to supremum of norm x less than equal to 1, norm of Tx. So this is so B stands for ball, okay, and this stands for sphere. Okay, so S stands for sphere and B stands for ball. So from definition, it is clear that so from a definition, it is clear that this norm of Ts is always less than equal to norm of Tb, because the supremum is taken over a bigger set. Okay, and this will be less than equal to what? From star, if I take supremum over less norm x less than equal to 1, so this is less than equal to m. Okay. So C star, from star it follows. So that means this norm of Tb is finite. This is finite because m is finite, and consequently this is finite. Okay. Okay. Now, so this is what I have proved, that I define norm of T as supremum over norm x is equal to 1, norm of Tx, and what I uh, define norm of Tb is supremum of norm x is less than equal to norm of Tx. So norm of Tx is less than equal to norm of Tb, and if I take supremum over norm x less than equal to 1, this is less than equal to not, so from here star you will get norm Tb is less than equal to m. Okay. Okay, so this is clear. So now let 0 not equal to x belongs to Rn. So like let y is equal to really x by norm x. So this implies this norm of y is really 1. So this will imply that t of y, norm of ti y is less than norm of ts. Okay. So if I put this thing, so this will give you t of x by norm x in place of y. If I put this is less than equal to norm of ts, so this will give you this norm of tx. I use the fact that t is linear. This is the norm of ts into norm x. So using this, so if I will take this thing, the supremum of norm x less than equal to 1, oh, norm of tx. So this is will supremum of norm x less than equal to 1, norm of ts. So this is really left hand side, this thing, whatever this thing, this is nothing but norm of Tb. Okay, so I will get that norm of Tb is less than equal to norm of Ts. Okay, so I'm calling this as B, say. I'm calling this as C. Okay, so from B we have this norm of T is less than equal to norm of T. See? So from B and C, it follows that norm of TS is equal to norm of TB. Okay. Okay. So now I have a new definition. So for T belongs to L, Rn, comma, we define operator norm of T to be operator norm of T. So this, since T norm of Ts is equal to Tb, and what is norm of Ts? The supremum of norm of x is equal to 1, norm of Tx, and norm of Tb is equal to supremum of norm x less than equal to 1, norm of Tx. So I define norm of T is equal to okay. So by I define this thing, so norm of T is really supremum of norm x is equal to 1, norm of Tx, this is equal to supremum. Okay. So this I, without verifying this thing that this is a norm, I am calling this as norm, but we'll shortly verify this. Okay. Okay. Now, okay. So now the thing is, so first observation. So from this thing, from D, so norm of Ts is equal to norm of Tb, and this is nothing but norm of T, operator norm by definition. Okay. From C, actually from D. Okay. First observation, I call this what observation A. From D of free space, it follows that this thing norm of Tx is less than equal to operator norm of T to norm of x. Okay. The second thing is B. From, okay, so suppose Tf, no, Tx is less than equal to m into norm of x. Okay. For some m. So then this will imply that operator norm of T is less than equal to m. This is clear. Okay. Now, okay. Okay, so let us prove this thing. Okay, so we okay, so since this we have proved that from B, this norm of TB is finite, norm of TS is finite. So this from B it is follow that norm of, so see, so from B it follows that operator norm of T is finite. Okay, so let us prove this fact that that operator norm is a norm. So first proposition. Okay. So proposition. So operator norm is a norm on LR. Okay. First thing. Second thing I want to draw. Let suppose T1 is a norm from Okay, so suppose okay, suppose let T2 is a mapping from this thing. Say Rm to Rn, and this T1 is a norm from Rn to Rk with two linear maps to LMs. LMs means linear maps. Okay, so if I composition this thing T1 composition T2, if you look at the operator norm, then norm of T1, so operator norm of T1, operator norm of T2. Okay, so LM stands for linear maps. Linear maps. Okay. So operator norm is a norm on this thing. Let T2 be a map from Rn to Rn, be a linear map, and T1 Rn to Rk be linear maps. Then the proof is so proof of the thing. So this proposition has two parts. So proof. First was suppose this norm of t is equal to 0. Okay, first thing is clearly this by definition this norm of t by definition norm of t is really greater than equal to 0. Suppose norm of t is 0, then by b, okay, so let us call this as star. Okay, so by star of previous space, look at the star here. This is the my star. If not, this is 0. If this is 0, the norm of tx is equal to 0, right? The star of previous space. So tx is equal to 0 for every x belongs to Rn. This implies t is equal to 0. Okay, so positive definition is done. Now what is alpha t? Norm of alpha t. So first thing is done. So norm of alpha t operator. So this is suprema for norm x less than is equal to 1. Alpha t norm. This is really modulus supremum of norm x less is equal to 1. Modulus of alpha norm of tx. This mod alpha can be pulled out. This suprema of norm x is equal to 1 norm of tx, and this is really nothing but mod of alpha norm t, where alpha belongs to R. Okay, so t belongs to L. Okay, okay. So this is the thing. So this homogeneity is done. So positive definite we have done homogeneity, triangle inequality. So this thing is suppose T1 plus T2 x. Okay, so this is norm. This is by definition, this is T1x plus T2x norm. And this is less than equal to norm of T1x plus norm of T2x. and norm of T1x, this quantity is less than equal to norm of T1 norm x. So what I'm saying, norm of T1x is less than equal to norm of T1. This is observation 1 or something. Oh, this is the thing for A. Similarly, this norm of T2x is less than equal to norm of T2 norm x. So this will be norm of T1 plus norm of T2 bracket norm x. Now this is the thing. I told you simple observation. If suppose norm of Tx is less than equal to m norm x, the norm of T is less than. Okay, so that will give you this thing, norm of T1 T2. Okay. Okay. This is by this thing B. Okay. So this is clear. So triangle equal to, so operator show this norm is a norm on LRN comma Rn. Okay. This is clear. So that we have proved the first thing. Second part is very clear. If you look at this thing, T1 composition T2. Okay, so if you T1 composition T2x norm, you take this thing. This is T1 of T2x operator norm. This is still be less than equal to norm of T1 T2x norm. I am applying this thing. T1y norm is less than equal to norm of T1. I am applying this thing. This star. So this is equal to norm of T1. Norm of T2x is less than equal to norm of T2. Okay, so this will imply that operator norm of T1, T2, norm of T1, norm of T2. So we have proved this thing. So operator norm on Rn is a norm on Lrn comma Rn. And if T2 is a linear map from Rn to Rn and T1 is a linear map from Rn to Rk, then operator number of the composition is less than equal to norm of T1 is less than equal to norm of T2. Okay, okay. So this is I have done. Now, okay. So we have proved this thing. Now, this thing LRN comma RM. This is really MNR. It has so M cross NR. Sorry. So this is nothing but RMN. So you can borrow the norm structure of RMN. This is really called Hilbert's Smith norm on this LRN comma RM. Okay. RM. Okay. Now we have another norm here. This is really, there are two norms. One is Forbenious norm or Hilbert-Smith norm. Okay. Okay. So Hilbert-Smith norm or Forbenious norm. One is this. norm, and another is really what operator norm. So this LRn comma Rn is a finite dimensional vector space. So any two norms are equivalent. So topology is really same. So it we will mostly work on operator norm, but because the thing is that is a most natural norm to really act on a most natural norm on this thing. Okay. Okay. So this is the thing. Now. Okay. So okay. So now let us exercise, or I will give an observation. So yeah. So exercise, or so let us look at the exercise. So let f from Rn to Rm be a function. So let fx is really f1x, f2x, fmx. Okay, so fx, so this fi is are really coordinates of f. Okay. So f is, so exercise is f is continuous at a belongs to Rn if and only if fix, so 1 less than equal to I less than equal to m is fi. Okay, this 1 less than is continuous at a. So if Rn to Rm be a function, let fx is equal to f1x, f2x, fmx. It says that f is continuous at a belongs to Rn if and only if the coordinate functions are really continuous at a. Continuous at a. Okay. Okay. So now, okay. So we know that. So we have this thing. So let us. So discussion. So okay. First discussion. Okay. So okay. I want to give a definition first. So definition. You know this MNR is really what this T from Rn to Rn. So that T is a linear map. Okay. T is LM stands for linear. Now this GLNR. What is GLNR? GLN by definition T from Rn to Rn. So that T is a invertible linear map. So that is this is same thing. T belongs to MNR. So the determinant of T is non-zero. So GLNR has so what is the topology of GLNR? But so GLNR is equipped with subspace topology of MNR. So what is the topology of MNR? Either you can get the topology. You can either you can induce a topology from operator norm or Hilbert split norm on MNR. Okay. Okay. So GLNR is T belongs to MNR, so that determinant of T is non-zero. Okay. So now, so first proposition, we want to prove that. So GLNR. Okay. So let us make it a small I. So GLNR is an open subset of MNR. Second thing is the mapping A going to A inverse is continuous on GLNR. So let us. The proof is very simple. So proof is I. So if you look at this thing, if we look at the thing determinant map, this MNR to the R, this is continuous. Why? Because determinant map is nothing but so okay, determinant of why this is since for any A belongs to MNR, so determinant of A is a polynomial in entries of A. This is clear. So I am saying this since for any behavior to A belongs to MNR, determinant of A is a polynomial. Therefore, this determinant map is MNR to MNR is continuous. And what is GLNR? GLNR is nothing but inverse image of R minus 0. And this R minus 0, this is open in R. Therefore, GLNR, inverse, since the determinant is continuous, inverse image of open set is open. So this GLNR is open in MNR. So inverse image of open set is open in. So this is clear. Second thing is also clear. So look at so if A belongs to GLNR, how does one prove finds A inverse? A inverse is so if you have A inverse is nothing but adjoint of A by determinant of A. What is adjoint of A? So adjoint of A is really transpose of the cofactor matrix. So if you look at this Cij is a cofactor. The Cij transpose and Cij is really what? This is cofactor. And how does one get that cofactor? By removing this ith row and jth column and then takes the determinant. Okay. So this each Cij is a continuous function. This is a polynomial in entries of A. So each Cij is a continuous function. Okay. So this that means this Cij is a polynomial in entries of A. So that means A going to adjoint of A is continuous. And you know that on GLNR, so A going to determinant of A is continuous. We have seen that in A. So that means A going to adjoint of A and determinant of A is non-zero in GLNR. So this A going to adjoint of A by determinant of A, which is nothing but A inverse. This is continuous. Hence A going to A inverse. It's continuous on GLNR. Now, okay, so I have really proved this thing. Okay, so this proposition is perfectly fine. Okay, so but we want to prove this proposition in a different way. And why do we want in a different way? Because the thing is, as I said, that one can also develop calculus on um, nonlinear spaces. Okay, for that reason, actually, uh, and this proof will not generalize to calculus on norm linear space, or this proof will not generalize for Banach algebra. So we have to will really prove it different way. Okay. Okay. So okay. Okay. So what? So what is the meaning of this? So okay. So this thing. So GLNR is open in MNR. What is the meaning? So meaning of this statement is follow. Meaning is this: given this, so that means any point of GLNR is an open set. So given any point B in GLNR, we will find a ball around B, so that ball will lie inside GLNR. So what is meaning? Meaning given X belongs to GLNR, so there exists some Rx positive number, so that Rx greater than 0, so that if X minus A is less than Rx, that will imply that A belongs to GLNR. Okay, so this is the meaning of. So first, actually, we will. Okay, so what is our goal? So this is our goal. Our goal is really given any X belongs to GLNR, there exists R greater than X than 0, so that if norm of X minus A is less than Rx, then this will imply A belongs to 0. Now, okay, so what happens if X is identity? So if what will be Ri in this case? So those who are really watching my video should pause for a second and should think. Okay, so Ri will be 1, because in case of GLN1, if n is equal to 1, this is really suppose I is equal to 1, and if something like Z minus 1, if Z is really lies in between this, if Z minus 1 is less than 1, then Z is invertible. Z is non-zero, right? So we will use this intuition, this thing, okay, uh, to think. Okay, so what I'm saying that, so okay, if X is equal to identity, so what will be Ri? Okay, so in this case, and you will. So it is easy to guess that this Ri will be 1, because the thing is GL and 1 are case. If you take n is equal to 1, GL 1R is nothing but R minus 0, right? So if, and what is identity? That's 1. So if Z minus 1 is less than 1, then that will imply that Z is non-zero. So that will say that Z is invertible. Okay. So, but the thing is, this is just an intuition. Let us prove it. So let us proposition. So we will give this proof of proposition a different way. So proposition. First, let A belongs to GLNR. If so, I am proving the same proposition. If norm of A minus I less than 1, this implies A is invertible. Okay. 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 So let us not. Okay. Proof is. So what is the idea of those who are looking, watching my videos online? So think and prove this on your own. Okay. So first. So what is the meaning of A is invertible? So remember, is we are in finite dimensional space. So I have only the estimate of norm of a minus I in my hand, that is less than 1. I have to use this information. So since I am in finite vectorial space, suffices to show so that A is really 1 1. Okay, that is AB is not equal to 0 for any A not equal to 0. Okay, okay. Now what is this thing? Okay, so let 0 not equal to V belongs to Rn. So this norm of A minus IV norm is less than equal to A minus I operator norm B, and this is less than 1. So this is less than 1. So this will be, so this quantity is strictly less than norm of B. Okay. So remember, I have to prove that norm of AB is not equal to 0, or any B is not equal to 0. So I estimate this norm of AB. Okay, so this is equal to what? AB. Okay. Okay, so this I write like this: the B minus. So this is really I minus A. Yeah. Because this is something same thing as I minus A. Hmm? So now this is from triangle inequality. You know that this is less than. I've given you some x. This is greater than equal to norm of B minus. No. See, the thing is, I minus in B norm is strictly less than norm B. So so this is strictly less than norm B. So this will imply that this is strictly greater than 0. And since B norm is strictly less than, so that means so this will imply that A B is not equal to 0. That means A is 1 1. So that means A is invertible. So okay, so we have proved this thing. Now the thing is, so this proof will also not generalize to the finite dimensional, infinite dimensional non-linear spaces. Because why? We have really utilized one fact that A is infinite dimensional vector space. If something is product is from Rn to Rn is 1 1, then it is invertible. So this fact actually we have utilized, and this is not true for infinite dimensional non-linear space. So we will do it in a different way. Okay, so we will prove this thing. Okay, so the thing is here actually in this proposition it say that only say that A is invertible, but it doesn't really say anything about the inverse. Okay, so we will in the second proof we will prove this proposition in a different way. In the second proof we will find an explicit inverse of explicit uh, expression of A inverse. Okay, so okay, what is the idea of the proof? So idea is very pretty clear. Okay, so idea is you look at Z belongs to C. So I have this thing, this I have a power series expansion. That is So Z belongs to C. So you know that I have something like 1 by 1 minus Z. Can be as a Power series expansion 1 plus Z plus Z square plus ZQ, something like that. And this is right hand side is convergent, mod Z less than 1. So I can write this thing 1 minus Z inverse is equal to 1 plus Z plus Z. Okay, so this is Z to the power M, Z to the power K, say K is equal to 0 to infinity. Okay, so this is valid for mod Z. Okay, call this as A. Okay, so what I'm saying, if mod Z is less than 1, the series K is equal to 0 to infinity Z to the power K, this is absolutely convergent, and this is equal to 1 minus Z inverse. So this happens for complex plane. So for MNR, if okay, so if Z is really looking at this thing A, so take we will we will get some idea for this MNR case. So this is the thing for complex plane case, and we want to imitate the same idea for MNR. So what I'm saying that if J mod Z is, suppose Z belongs to MNR and mod norm Z is less than 1. Okay. By looking at A, by looking A, we hope that, okay, if mod Z is less than 1, this series K is equal to 0 to infinity Z to the power K, okay, our is convergent. This I minus Z, okay, I minus Z, okay, is invertible. Invertible. And third thing is I minus Z inverse is nothing but, okay. So what I'm saying that for complex plane we have a series like this. So looking at this thing, we want to generalize that this series for MNR. So you take Z belongs to analogously, we take Z belongs to MNR and mod Z. So our guess is that if more operator norm of Z is less than 1, okay. So this series K is equal to 0 to infinity Z to the power K is convergent, and 1 minus Z is invertible, and 1 minus Z inverse is equal to K inverse is equal to this thing. K is equal to 0 to infinity Z to the power K. Okay. Okay. So, and how does this will help? So remember, our goal is to prove this proposition. Okay. Suppose you, okay, I suppose this is true. Okay. So in fact it is true. Okay. So how this will help in your proposition? So in our proposition, we will put simply Z is equal to I minus A, because it is given that norm of I minus A is less than 1. So if I will put Z is equal to I minus A, so I will get, if I will put Z is equal to I minus, I will get this A inverse. Okay, A inverse is equal to this thing, K is equal to 0 to infinity I minus A to the power K. That's simple. Okay. Okay. So okay, so this is our usefulness. So let us prove then. This is first lemma. First lemma into proof. So let Z belongs to M and R. Okay. B says that. So operator norm of Z is less than 1. And okay, then the series, okay, K is equal to 0 to 1 infinitive Z to the power K is convergent. In fact, something it is much more than convergent. This is absolutely convergent. Okay, okay. First thing, and I minus J. Okay, so I minus Z is invertible with I minus Z. Inverse is really K is into infinitive 0 to. Okay, proof. So the thing is, I told you that operator norm of T1 composition T2 is really is less than equal to operator norm of T1 operator norm of T2, right? Now if you put in place of T1 and T2, if you put Z, so this is Z square, operator norm of Z square is less than equal to, you will get that operator norm of square of the operator norm of Z square, operator norm of Z square. So similarly, if you will get this operator norm of Z3 is less than equal to. Okay. So this will give me the operator of Zk is less than equal. Okay, so this is clear, right? Now the okay, so operator of Zk, you will get that. Okay, okay. So clearly this thing. So let okay, let this thing Sm is equal to K is equal to 0 to M Z to the power K. Okay, so this is a this belongs to M and R. Okay. Okay, so now what is Sm minus Sl? Okay, so suppose suppose this. Okay, so let us see Sm minus Sl. Okay, so so this is okay, so suppose assume so let M is less than L, then this is thing Sl minus Sm. So this is what this is K is equal to 0 to L Z to the power K minus K is equal to 0 to M Z to the power K. So that will give you K is equal to really M plus 1 to L Z to the power K. That means SL minus ASM norm. So this is equal to K is equal to M plus 1 to L Z to the power K norm. Okay, so this is totally less than equal to K is equal to M plus 1 to L norm. So this will implies me Now I can use this thing norm zk is less than a norm z to the power k. So this is k is equal to m plus 1 12 norm z to the power k. So this is really less than equal to norm z to the power k. K is equal to m plus 1. So this is strict for the less than equal to k is equal to m plus 1 to infinitive mod z to the power k. So this is nothing but z to the power m plus 1 by 1 minus z. Okay, so this is okay. Okay, so that will give you that if m tends to infinitive, so this is limit m tends to infinitive, same this is 0 because mod z less than. So that will give you from this thing that this SL so SM m belongs to n is a Cauchy sequence. So that means SM as m belongs to n is a Cauchy sequence. So this is that means and this MNR is a complete because it is a I have told you that as MNR is complete. So there exists B belongs to MNR. So that this B is equal to limit m tends to infinity Sm. And what is Sm? This is the thing is it is z to the this is B. This is z to the power k is equal to 0 to infinity. Okay. 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 So this is the thing. So okay. So what I have to show that I minus j. Okay. So B is I have this. So first what I have shown this this series actually convergent. This series is convergent. I have shown. Okay. Now what I have to show that so I minus z. So I minus z into Sm. So this is really I minus z, and what is Sm? This is k is equal to 0 to m. So this is zk. So if I multiply that, this is I will get this k is equal to 0 to m zk. And if I multiply minus z into zk, so this is k is equal to 0 to m z to the power k plus 1. I look take this thing 0 to m z to the power k. Man, I do the indexing starting from 1. So k plus 1 will be my new k. So that you can write it as k is equal to 1 to m plus 1 z to the power k plus j to the power k. So that will give you what I minus z to the power m plus 1. Okay. Okay. This is clear. Now I can take limit k m tends to infinity in both sides. I minus z into s. Okay. So let us. Okay, if I take limit both side m tends to infinity, taking m tends to infinity in both side, we get this thing limit m tends to infinity I minus z into Sm is equal to I. So limit m tends to infinitive, I minus z to the power m plus 1. Okay, so this is really I minus limit m tends to infinitive z to the power m plus 1. Now look at this test. I have norm z to the power k is equal to norm z to the power k. So this will, and norm z is less than 1. So this will imply that limit k tends to infinitive, norm z to the power k is equal to 0. So that will imply that limit k tends to infinitive, z to the power k is equal to 0. Okay, so so this is star. Okay, so what I'm saying that limit k tends to infinity mod z to the power k is equal to 0. This will imply limit k tends to infinity z to the power k is equal to 0. I can call this as, so this is star. Okay. So this thing is 0, right? As m tends to infinity, this thing is 0. This thing. So this will, I will get to I. Now this matrix multiplication is so what I'm getting, limit m tends to infinity I minus z. So this I minus j, since matrix multiplication is a continuous function, so I can take the limit inside. So this is limit m times infinity Sm is equal to I. So the reason is here, matrix multiplication is continuous. Since matrix multiplication is continuous, so this will imply that I minus z and limit m to infinity b is equal to 1. Okay. So what will happen that so what I am getting, this I minus z is b into b, and b, what is b? This is b is equal to k is equal to 0 to infinity to the. So this will imply that b is equal to, oh, so this implies I minus z inverse is equal to b, and b is equal to what? K is equal to 0 to infinity. So this is equal to k is equal to 0 to infinity. Okay, so this I have proved that I have proved the lemma. Okay, so now there are two remarks. So first remark is one. In case of infinite dimensional vector space, so infinite, okay, the dimensional, say Banach culture, I do, okay, non-linear space. I told you that this proof doesn't uses one thing, that this the so this proof will generalize to really Banach algebra. Okay, so infinite dimensional normal algebra or something. So only one thing actually extra, one thing, norm linear space, or Let us write Banach algebra. So I will not define what is Banach algebra. I am just saying it. So Banach algebra. So only one thing you have to prove this. Um, one thing we have to add in the proof, that b into I minus z is I, and which is exactly proved in the similar way. Second thing, okay. Second thing I will take in exercise. So what is I minus z inverse? I minus z inverse is really 1 plus z plus z square plus z cube. So this is really nothing but I plus z, and this is really big O of z square. Big O for norm z square, right? Okay, big O of z square. No, this is. And similarly, this is same thing as y plus z plus z square. This is exactly the same thing as O bar. Big O of norm z square. Okay, so this is an exercise. Yeah, it is an exercise. Yeah, no. Okay, so this. Okay, so let us write this thing. I plus j plus big capital O norm z square, right? Okay, so this is an exercise you can do. So being at the proposition, coming back. So what was our observation proposition? So proposition. So let A belongs to GL and R. This is that norm of I minus A is less than 1. And then this thing, the series M is equal to 0 to infinity A minus I to the power A. Sorry, I minus A to the power M. This is convergent. And I minus A is invertible. With this thing, I minus A inverse is equal, oh, sorry, A is invertible with A inverse is equal to. Proof is apply the previous lemma with z is equal to I minus A. Okay, so I have proved the proposition once more. So we gave three different proofs of this fact that. Okay, so you gave two different proofs of this fact that if norm of A minus I is less than 1, then A is not. So with this, I would like to stop here. Okay, so the thing is, do subscribe my channel, and if you have any question, please. Okay, so let us stop there, and do subscribe my channel and like and share this video if you find it is helpful. Okay. Okay, so let us stop the video and let us stop this lecture also.